Hello everyone, today I want to talk about the magnetism. As you know that magnet attract the magnetic material, and magnet has north pole and south pole. Okay, so the magnet, this is a bar magnet, it has a north pole and south pole. Every magnet, they have a north pole and south pole. But if you cut the magnet right here, so it results two magnet. So this is north pole, the south pole developed here. So this is a new magnet. Then the other piece here, this is also the magnet. So here you have a south pole and this is north pole now. So if you break this magnet, the result is you get two magnets there. If you break it again, you get another two magnet like this. Okay, so if you break like if you make it really tiny, you still have a north pole and south pole. That means magnetic monopole never exists. Magnetic monopole never exists. If there is a north pole, there must be the south pole. Okay, and the current produced the magnet. This is Oersted discovery. So current produced the magnet. Let me explain more about it. Let us suppose you have compass needle. This is the compass needle, and you keep the compass needle here. This is the compass needle, okay? And right here, this is a wire. This is resistor. You have battery here. You can keep the switch there. Okay, so this is switch, this is battery, this is resistor, and here you have a compass needle, and you know that compass needle always points north and south. Okay, so in this case, this compass needle points north and south. There is no current in the circuit because the switch is off circuit here. The circuit is open circuit, and this compass needle points north and south. But if you close this switch, now the circuit is closed circuit. Current passing through the circuit. So there is a current I. So if the current is passing through this circuit, right here, there is a current. Then in this case, what happened is the compass needle, it does not point north and south. It deflects. Why? Because this current, the current here in the circuit, produced the magnetic field there. So you have a magnet here, right? The magnetic field right there. So this magnetic field is responsible to deflect this magnet, compass needle. That means the current produced the magnet. Is reverse true? It's magnet produced the current then? We'll talk about it in Faraday's law of electromagnetic induction. So for now I can say yes, but there is some condition. There is some condition. Okay, only the changing magnetic field produces the current, but simply if the magnetic field is like a uniform, then in that case no current produced there. But here the current produced the magnet, and this is the Oersted discovery. Okay, so the current produced the magnet. That means there is a magnetic field. Current produces the magnetic field, and magnetic field is a vector quantity. Okay, magnetic field is a vector quantity. Simply the magnetic field is represented by B, and it is the vector quantity, and the unit is Tesla. Okay, so if the magnetic field is a vector quantity, then we have to give the direction of magnetic field. For example, let us suppose this is the conductor. This is the conductor, and this conductor carries the current. Okay, so consider this is conductor, and this conductor carries current in this direction. And we already discussed current produces the magnet. That means there is a magnetic field here. So how do you figure out the direction of magnetic field then? Okay, now look at this. We have the right hand rule. Okay, we call RHR number 1, right hand rule number 1. So what is the right hand rule? Suppose this is the conductor carrying the current, and the current is upward direction. So use your right hand, grab this conductor such a way that the thumb, you see this thumb point in the direction of current. So this thumb points in the direction of current, and this curl finger gives you the direction of magnetic field. That's it. So thumb points in the direction of current. The thumb points in the direction of current, and this curl finger gives you the direction of magnetic field. So simply the magnetic field encircle the current, or you can say the magnetic field encircle the current carrying conductor. So the magnetic field is like this, or you can draw here also. So this way. So this is the magnetic field. Magnetic field encircle the current. So this line. Actually, this line is magnetic field line, or simply you can say magnetic lines of force. This line. This is the closed loop. This is magnetic lines of force is closed loop. This is the field line, magnetic field line, or you can say magnetic lines of force. So how do you get the direction of magnetic field right here then? If you draw the tangent at any point on the magnetic lines of force, that gives you the direction of magnetic field, or simply you can say that gives you the magnetic field. So right here, if you want to find out the magnetic field right here, draw the tangent like this. So this gives you the magnetic field right here, because the magnetic field is defined at a point. Okay, so at this point the magnetic field is B. So simply this tangent gives you the magnetic field. If you want to find out the magnetic field right here at this point, draw the tangent here. So this tangent gives you the another magnetic field right there. If you want to figure out the magnetic field right here, draw the tangent then. So this is also the magnetic field. So simply if you draw the tangent line at any point on the magnetic lines of force, that magnetic lines of force gives you the that tangent line gives you the magnetic field. Okay, so this is the right hand rule number 1. So simply if the current is straight, then the magnetic field is like this. Actually this is the magnetic lines of force, because if we can draw the magnetic lines of force, then we can find out the magnetic field, because the tangent at any point on the magnetic lines of force gives you the magnetic field. Okay, so if the current is straight like this, look at this, this is the current, straight current, then the magnetic field is simply, this is the magnetic field, this one. Use your right hand, always use right hand. So thumb point in the direction of the current, and this finger gives you the direction of the magnetic field. So if the current is down, then again use the right hand rule this way. So this thumb gives you the direction of current, and this is your magnetic field. This is how you have to use the right hand rule number 1 to figure out the direction of magnetic field. Okay. So if the current is straight, the magnetic field is circular. What happens if you have the current like this? So let us suppose this is the current. The current is circular. Here we use the right hand like this. Here in this case, this is your thumb, and here. So thumb points in the direction of the current, and the curl finger gives you the magnetic field. But right here, the current is circular. So how do you get the direction of magnetic field then? In this case, the magnetic field is in this direction then. This is the magnetic field. Straight current, magnetic field is circular. Circular current, magnetic field is straight line then. So this is how you have to figure out the direction of the magnetic field. Okay. So again, this is Oersted discovery. The current produced the magnet. Okay. And another point I'd like to talk here is, I use the word magnetic lines of force. If you have magnet, bar magnet, it has a north pole and south pole. The magnetic lines of force start from the north pole, like this. Don't say the magnetic lines of force terminate at south pole. No, magnetic lines of force is a closed loop. So you can draw if you want inside the magnet also. But nobody interested to draw the magnetic, this line inside the magnet. But the magnetic lines of force is a closed loop. Okay, but it starts from the north pole. So this is how you have to draw. If you want to draw another line, you can draw like this. You can draw as many as you want. If the magnet is strong, then you have a many magnetic lines of force. Okay, so these are the magnetic lines of force. Magnetic lines of force forms the closed loop. Okay, magnetic lines of force start from the north pole, and it forms the closed loop, number 1. Number 2, if you draw the tangent line at any point on the magnetic lines of force, for example right here, this is a point, and if you draw the tangent here like this tangent line gives you the magnetic field at this point. Again, the tangent line drawn at any point on the magnetic lines of force gives you the magnetic field at that point. This is the second point. The tangent line the tangent line drawn at any point on the magnetic lines of force gives you the magnetic field at that point. Second point. And third point is, 2 or more than 2 magnetic lines of force, they never intersect to each other. Two or more than 2 magnetic lines of force never intersect to each other. Why? Because it is like this. If you draw magnetic lines of force, let's say, and here as the, let's say one magnetic line support is this. Another magnetic line support, if you draw like this, look, these two lines of force, they intersect right here. What happened? I told you that the tangent line drawn at any point on the magnetic line of force gives you the magnetic field. That means, look, this point is common to both lines. So if I draw the tangent on this line, so I have a tangent like this. And if I draw the tangent on this curve, then I have a tangent like this. That means I have a two tangents. That means two magnetic fields. That is not possible. That is why two or more than two magnetic lines of force, they never intersect with each other. Okay? So these are the properties of the magnetic line support. Simply, if you want to make more points, you can write down yourself. Like the magnetic line support, they are crowded near the pole. The concentration is more near the pole. That means the magnetic field is bigger near the pole. Okay? And the magnetic field line, they normally emitted from the north pole also. So if you want, you can make another point there. Okay. I mentioned that the current produces the magnet. So let us suppose I have wire. This is the wire. This wire carries the current I. And now we know that current produces the magnet. That means the current produces the magnetic field. And I want to calculate the magnetic field right here. And at this point, let me call this is a point P. I want to calculate the magnetic field at this point, and let us suppose this point is at a distance r from the current, at a distance, perpendicular distance, at a distance r from the magnet. So as we know that the magnetic field is circular like this, right? Using the right hand rule, so the magnetic field is this, circular magnetic field. So this point P, which is at a distance r from the conductor, from the current, so I want to calculate the magnetic field right here. So of course, if the magnetic field line is circular like this, and I have to calculate the magnetic field right here. So if I draw the tangent line right there, so this is your magnetic field. So how do you calculate this B then? It is observed that the magnetic field B at this point is directly proportional to the current here. The magnetic field is directly proportional to the current and inversely proportional to the distance r. These are. Again, the magnetic field at point P is directly proportional to the current. So how big current you have there? So magnetic field depends on this current directly proportional. And this magnetic field is inversely proportional to this length, this distance r. This means if you come closer, if this point is close to the current, magnetic field is big. If you move this point somewhere there, far from the current, the magnetic field is small. Therefore, again, the magnetic field is directly proportional to the current and inversely proportional to the distance of that point from the current, but it is a perpendicular distance. Okay, so B is proportional to I over R. Then I want to remove this proportionality sign and I want to put equal sign here. So write down equal, and here mu 0 divided by 2 pi. This is the constant I over R. So this is the formula to calculate the magnetic field due to the current carrying conductor. So this is a conductor, this wire is a conductor, so I can say this is current carrying conductor. And if you want to calculate the magnetic field at any point, you can use this formula. Here R is the distance of that point, perpendicular distance from the conductor, okay, from the current. And of course here I is the current in the conductor and B is the magnetic field. Again, the unit of magnetic field is, we use Tesla. If you want to use a smaller unit, the smaller unit is Gauss. Tesla is, like a meter, we use a Tesla. If you want to use like a smaller unit like a centimeter, you can use Gauss. So the one formula to calculate the magnetic field is B, this is equal to mu naught I divided by 2 pi R. Now here, you know the pi 3.14, but what is mu 0? It is constant, and mu 0, this is 4 pi times 10 to the power negative 7 Tesla. T is the Tesla meter per ampere. So again, it is better to remember this number, mu 0, which is equal to 4 pi times 10 to the power negative 7, and the unit is Tesla. T is the Tesla meter divided by area. So Tesla meter per, not area, Tesla meter per ampere. Again, this is not area, okay, this is ampere, unit of current. 4 pi times 10 to the power negative 7 Tesla meter per ampere, and this is called as the permeability of free space. What is permeability then? This is the response of the medium, here it is the free space, the response of the medium to the magnetic field. That is what we call the permeability. Okay, so permeability is 10 to the power negative 7 times you have a 4 pi Tesla meter per ampere. Okay, so this is the one formula to calculate the magnetic field. Okay, so this is the magnetic field due to the current carrying conductor. Okay. Now let's discuss about the force experienced by current carrying conductor in the magnetic field. New topic. Force experienced by the current carrying conductor in the magnetic field, inside the magnetic field. It is experimentally found that if we keep the conductor, this conductor inside the magnetic field, but this conductor must carry the current. Okay, so the current carrying conductor inside the magnetic field. Okay, so if we keep the current carrying conductor inside the magnetic field, that current carrying conductor experiences the force, or in another word you can say that the magnetic field exerts the force on the conductor, current carrying conductor. So let us suppose you have magnetic field here. This is the magnetic field B, okay, and consider this is a conductor, but there is a current, okay. This is a conductor, and you can connect to the some kind of source here, something like this. But the length of this conductor is L. L be the length of the conductor. L, length of the conductor inside the magnetic field, and consider there is a current here. Current is I. I be the current. I be the current passing. So I be the current passing through the conductor, and of course P is the magnetic field. It is uniform magnetic field. Uniform magnetic field. And let us suppose there is a current here, so this angle theta, theta is angle between the current and the magnetic field. Okay, theta angle between current and magnetic field. Okay, so again it is experimentally found that this conductor experience the force, or the magnetic field exerts the force on this conductor, and the force experienced by the conductor at this is, it depends on the current I, it depends on this length also, L, it depends on the magnetic field B, and it depends on sign of angle between the magnetic field and the current, sine theta. So the force experienced by the current carrying conductor inside the magnetic field F, this is equal to I L B sine theta. So if you increase the current, force increase. If the length of the conductor inside the magnetic field is long, the force is big. If the magnetic field is also big, then in that case also the force is big. And it also depends on the angle between I and the B. It depends on angle between the current and the magnetic field. So in this case, when do you get the maximum force then? You know, the sine theta, the function, sine function, the maximum value of sine function is 1. If theta is equal to 90 degree, then sine 90 degree is equal to 1. So you get maximum force F max, this is equal to I L B. This is the maximum force experienced by the conductor inside the magnetic field. That means if this conductor is like this, perpendicular, if it is like this, perpendicular, theta is 90 degree, like this. If the conductor is perpendicular like this, 90 degree here, then in this case, this conductor experiences the maximum force. Then what happens if the conductor is sitting parallel to the magnetic field like this, if the conductor is like this? So current is this, magnetic field is also in the same direction, that means the current and the magnetic field, they are parallel, that means the theta is 0. So if the conductor is sitting parallel to the magnetic field, that means the angle between the current and the magnetic field is 0. So in that case, what happens? If theta equal to 0, then you have to figure out sine 0 degree. So sine 0 degree equal to 0. Then what happens? F equal to I L B times 0. So everything is 0 then. So this is the minimum force then. 0 force, no force. Therefore, if the conductor is parallel to the magnetic field, no force there. Okay? And if you have some other angle like 20 degree, 30 degree, 40 degree, simply plug the value of theta here, then you can get the force there. Okay? So here we have a force, we have a magnetic field, we have a current. This is the current, okay? This is the current I. This is the current I. Force, it is the vector quantity. Magnetic field, it is the vector quantity. Current, it is not vector quantity, it is scalar quantity, but still we give the direction, like we can say clockwise, counterclockwise, plus to minus, like that. So we have to figure out the direction of the force then. We already talked about the right hand rule number 1, right? This one. If this conductor carries the current, the magnetic field is like this. We use the right hand rule. So the thumb is the direction of the current, and this curved finger gives you the direction of the magnetic field. This is right hand rule number 1. But here we have to figure out the direction of the force. And here also we have the right hand rule, and we call this is right hand rule number 2. So what is right hand rule number 2 then? So right hand rule number 2 Okay. Here we have to figure out the direction of the force, direction of the magnetic field, and direction of the current. Here too you use the right hand, so do this. The outstretched finger, this finger. This is the direction of current. This finger, the outstretched finger, you do like this. So this finger gives you the direction of the current. Now curl your finger. This gives you the magnetic field. This gives you the magnetic field. And the thumb gives you the direction of force. Thumbs gives you the direction of force. Again, this outstretched finger. Use your right hand. This outstretched finger gives you the current, direction of current. This curled finger now gives you the magnetic field, and thumb gives you the direction of the force. Okay, or you can do like this. Just if you want to use 3 fingers, I think this is easier to memorize. Do this. This is a force. Thumb gives you the force. This is your current, and this gives you the magnetic field. F force, I current, B magnetic field. Okay, so let me try to draw. I don't know if I can draw. It is something like this is the thumb, and this is your finger, like this. Okay, and something. This is F, this is I, this is B. My diagram is not quite good. Please look at the textbook also. So you can see here this. Okay, this is a current, this is a magnetic field, and this is the force, and this is the right hand rule number 2. Okay, it is important. You need to know this. So, and the formula is this gives you the magnitude of the force ILB sine theta. So the force depends on current, depends on length, but don't forget the length L is this length inside the magnetic field only. If this conductor is long, and then if it is extended somewhere there like this, but you have to measure the length only inside the magnetic field. Okay, so the force depends on length also, and it also depends on the strength of magnetic field, and of course the theta. Theta is angle sine of theta. Okay, angle between the current and the magnetic field. Okay, so this is pretty simple. Then we have a next topic kind of similar to this. Next topic is force experienced by moving charged particle in the magnetic field. Before we did the current carrying conductor, now we like to do the force experienced by the moving charged particle in the magnetic field. Why? Because if this is a conductor and if there is a current, that means the particle, charged particle is flowing, moving through this conductor, and actually that charged particle is electron there. So due to that moving electron, this conductor experiences the force. So if the charged particle is moving individually, then in that case also the charged particle experiences the force. So let us suppose this is the magnetic field, uniform magnetic field. I want to draw like this. This means if you have a cross mark like this, this means the magnetic field is into the page. This is B, magnetic field into the page. If you draw something like this, like dot, dot like this is magnetic field out of the page. Please note this, we need this in future also. magnetic field into the page, magnetic field out of the page. So I want to draw that. The magnetic field into the page, and the magnetic field is uniform. This is uniform magnetic field. And what are we doing here is we would like to calculate the force experienced by the moving charge particle. So inside the field, so I want to take one charge particle, simply let me take a positive charge like a proton, okay, and the speed of the moving charge particle is v, because look, up to this point, this line, there is no magnetic field. Now the charge particle enter into the magnetic field. Once it entered into the magnetic field, it experiences the force and it moves in a circular path like this. Okay, the force exerted by the magnetic field on the charged particle is here always perpendicular. So the direction is changing, always perpendicular. That means this path is circular path. Okay, and the force experienced by this charged particle F, this force depend on the charged particle itself, the charge. It depends on, let's say, proportional to the Q, the magnitude of the charge. The force experienced by this charged particle, it depends on, or you can say that directly proportional to the magnitude of charge. And the force, it also directly proportional to the speed of the charged particle inside the magnetic field. And the force is proportional to the strength of magnetic field B, and the force is also proportional to the sine of angle theta. What is theta here? Theta, this is angle between V and B. Okay, so the force exerted by the magnetic field on the charged particle is directly proportional to the charge, the magnitude of the charge. The force is again directly proportional to the speed of the charged particle. The force is again proportional to the strength of the magnetic field, and the force is also proportional to the sine of angle theta. Here theta is the angle between the V speed and the magnetic field. So here don't confuse, this is the force, F is the force, Q is the magnitude of the charge, this V is the speed, B is the magnetic field, and theta is angle between the speed and the magnetic field. Okay, and if you want to remove this proportionality sign, you can simply write down equal sign and write down Q V B sine theta. This is the formula to calculate the force exerted by the magnetic field on the charged particle. And there, here you have to put some constant here, but in this case the constant is 1, so it is not necessary then. So simply this is the force exerted by the magnetic field on the charged particle, QVB sine theta. Kind of similar to the previous case. Now here also, when do you get the maximum force then? Like if theta equal to 90 degree, then of course sine 90 degree equal to 1, and you get the maximum force is QVB. This is the maximum force experienced by the charged particle. That means if the charged particle is moving perpendicular to the magnetic field. So think like this. Let us suppose the ceiling is a north pole and the floor is the south pole. So the magnetic field is from north pole to south pole, so this direction, downward. So the magnetic field is like this. And if the charged particle is moving perpendicularly, in that case, the force experienced by the charged particle is maximum. Okay, so if the charged particle is moving perpendicular to the magnetic field, then the magnetic field exerts the maximum force in that case. Okay, if theta equal to 0 degree, that means sine 0 degree equal to 0. Then if you plug sine 0 here, so sine 0 is 0. Then if you multiply 0 and this number, everything is 0. This means the force is 0 then. Force is 0, no force. Okay, so if the charged particle is inside the magnetic field but no force, what does that mean? There are two possibilities. One possibility is charged particle is inside the magnetic field, it is moving parallel to the magnetic field. Parallel or anti-parallel also, 180 degree also 0, sine 180 is also 0, right? So if the charged particle is moving parallel to the magnetic field or anti-parallel to the magnetic field, no force on the charged particle. Or if this v equal to 0, if the speed is 0, that means the charged particle is at rest. In that case also the force is 0. So there are two things. One is if the charged particle is at rest, no motion inside the magnetic field, no force. Or if the charged particle is moving parallel to the magnetic field or moving anti-parallel to the magnetic field, no force. Okay. So this formula I can write down in different, I can use the vector notation also. Look at this. I want to remind you guys, if you have two vector A and vector B, if you take the dot product, this is the dot product, okay? Dot product A dot B, and this is simply magnitude of A, magnitude of B, cosine theta, and this is the scalar quantity. Dot product, the result is, if you take a dot product between two vectors, the result is scalar quantity. But if you take the cross product, this is the cross product, and this is, you can write down magnitude of A, magnitude of B, sine theta, then you can write down n cap. This is the unit vector. Okay, so this is a vector. So if you take a cross product between two vectors, the result is again a vector. Okay, so this is a cross product. Now if you want to use a vector notation, I have a formula F equal Q V B. If you don't write down, if you write down like this, F equal to Q V B sine theta, this gives you the magnitude. But if you want to write down in vector notation, write down vector F, and right here you have to write down n cap. So this gives you the direction of the force here. Okay, the vector there. Simply we use the right hand rule number 2 then. So look at this. A cross B is AB sine theta n cap. So Q is, look, this is a scalar quantity. Velocity, if we consider velocity here, velocity is a vector quantity. So what we can do is F equal, you can write down Q V cross B then. This is the vector notation. So this force is perpendicular to the plane of the velocity and the magnetic field. This force F is perpendicular to the plane of the V, the velocity, and the magnetic field. Okay, but simply if you keep this in mind, F equal to QVB sine theta, I think this is good enough for you in this class. Okay, but if you want to write down in vector notation, you can do this also. Okay, so this is the force experienced by the moving charged particle inside the magnetic field. Please don't forget the charged particle inside the magnetic field. If it is at rest, or if it is moving parallel to the magnetic field, or if the charged particle is moving anti-parallel to the magnetic field, no force. Okay. Okay. Few minutes ago we talked about the magnetic field due to the current carrying conductor. Now I want to talk about the force between two current carrying conductors. Okay, let us suppose you have the conductor, and this conductor wire has current I1, and this current carrying conductor creates the magnetic field like this, right, using the right hand rule. Let us take one point somewhere there, and this point is at a distance d from the current I1. Let me call this length, the length of this conductor is L1, and you can calculate the magnetic field at this point, right? The magnetic field created by this current I1 at this point is, let me call B1. B1 is, what is the formula? Mu naught I1 divided by 2 pi d, because the formula is, I gave you, like a B is mu naught I divided by 2 pi r. This is our formula. So I want to use this formula right here. I have a conductor having length L1 and current is I1, and I want to calculate the magnetic field at this point. This point is at a distance d from this conductor. So due to this conductor, current carrying conductor, the magnetic field here I use B1 is equal to mu naught I1 divided by 2 pi d. Over there I use I and r, but here I is I1, d is like r, you have a distance. Now I want to keep another conductor right there like this, and this conductor has a length L2, and the current here is I2. You already have a magnetic field B1 right here due to the current I1, and we recently talked about the force experienced by the current carrying conductor inside the magnetic field. So this current carrying conductor number, let me call conductor number 2, this is conductor number 1. Okay, so this conductor number 2 is inside the magnetic field of the conductor number 1. Don't confuse here. The conductor 2 is inside the magnetic field created by this conductor, which is B1. And if the conductor, current carrying conductor, is inside the magnetic field, that current carrying conductor experiences the force, and that force is F equal to I L B, the maximum force. Okay, I want to keep perpendicular to 90 degrees. So the force is I L B sine theta, but the maximum is I L B then. So this is the formula. This is the force experienced by the current carrying conductor inside the magnetic field. And here the conductor number 2, you keep the conductor number 2 inside the magnetic field B1, and this magnetic field B1 is created by I1. So in this case, if you use this formula, the force experienced by this conductor F equal to, the current here is on this conductor, in this conductor is I2 L2 B1. So B1 is magnetic field created by the conductor 1, I2 is current in the conductor number 2, and L2 is length of the conductor number 2. So F equal to I2 L2 B1. Okay, so this is, you can write down I2 L2 B1 is, you can write down mu naught I1 divided by 2 pi d. Okay, so you can write down F equal to, let me write down in simpler form, mu naught divided by 2 pi, then you can write down I1 I2 divided by d and L2. So this is the force, this is the force experienced by conductor number 2 due to this conductor 1. Force experienced by conductor number 2 due to the conductor number 1. Now, if this conductor experience the force, this conductor also experience the force then. How big force does this conductor experience here then? Go back to the Newton's third law. To every action there is equal and opposite reaction. Okay, so if this experience, for example, 10 Newton force, if this experience 10 Newton force, pushing or pulling force, whatever, it depends on the direction of the current. In this case, this is attractive force. In this case, the force is attractive. If the currents are in the same direction, then the force is attractive force. Okay, so this conductor experience, let us suppose 10 Newton in that direction. How big force this conductor experience then? 10 Newton in the opposite direction. Newton's third law, right? So the force experienced by this conductor is also equal to this much. You don't have to develop another formula here, okay? Because they experience equal and opposite force. And if the current is in the same direction like this, current ion upward, there is attractive force. If you have like this current is up, and if this current is down, then in this case the repulsive force like this. So this is the force, repulsive force. Okay. So this is the formula to calculate the force between two current carrying conductors, and they are parallel. I mean like this. I mean the distance between them. This distance is parallel. The current may be parallel or anti-parallel, but the wires, they are parallel. Okay. And if you want to calculate the force per unit length, like this, F, bring this L2 here, F over L2, then you can write down mu naught divided by 2 pi I1 I2 divided by D. Okay. So this is the force between two current carrying conductors. Okay. How do you get the direction, like a repulsive or attractive? First you have to figure out the direction of the current, then you can use the right hand rule. Right hand rule number 2. You can get the direction of the force. Okay. Guys, I think I forgot to tell you one thing like this. Uniform magnetic field, and if you have a moving charged particle, and if the charged particle is inside the magnetic field, then it moves in the circular path. Okay, and the force experienced by the charged particle F equal to Q V B sine theta. We already talked about this. Okay, so here you have a V, you have a B, you have the force, speed, magnetic field, and the force. Here also we have to give the direction. Okay, and here we have another right hand rule number 3 then. I was supposed to tell you before the force between two conductors, okay, but it's okay, we can discuss right here. So what is how do you figure out the direction of the force here? The force experienced by this charged particle, and the charged particle has a charge Q, and this is positive in this case. Okay. If it is negative, then the direction of the force is simply reversed. So again here we use the right hand rule, and the right hand rule is, use your right hand. This outstretched finger gives you the direction of velocity, speed. The outstretched finger, this is the direction of the speed. Curl your finger, this is the direction of the magnetic field, and thumb gives you the force experienced by the positive charged particle, like a proton. Again, this outstretched finger, this gives you the speed, velocity. The curl finger gives you the direction of the magnetic field, and this gives you the force acting on the charged particle, but it is positive, that this is good for the proton or positive charged particle. If it is negative charged particle, then simply the force is, you do this, like this. Okay. So again, This is force, this is V, and this is the magnetic field. This is right hand rule number 3. Okay, and one more thing, the charged particle is moving in a circular path, and the maximum force here is F equal to QVB if theta equal to 90 degree, right? If theta equal to 90 degree, this is the maximum force. But in general college physics 1, that is physics 120, we learned that if the object is moving in a circular path, you need a force to keep the object in a circular path. What is that force? That force is the centripetal force. So here also you need a centripetal force. So what is the source of the centripetal force here then? Simply the magnetic force, this one QVB, act as a centripetal force. Due to this magnetic force, the object, the charged particle is moving in a circular path. So simply here F, let me call this is F of B, this is a magnetic force, okay. This gives you the centripetal force F of C then, okay. If the charged particle has a mass m and speed v, mv squared divided by r is the centripetal force. mv squared divided by r, this is the centripetal force, right? R is the radius of the circular path, and this is QVB, magnetic force. If the charge is E, like electron, E VB, this is equal to mv square divided by r. This V and this V you can cancel out. So EB, this is equal to mv divided by r. If you want to divide by m on both sides, you will get AE over m. This is equal to V over RB then. So this is called as charge to mass ratio. This is, look, E is the charge, M is the mass. If it is electron, then you can do like this. E over m, this is E is 1.6 times 10 to the power negative 19 coulomb. M, mass of the electron, is 9.1 times 10 to the power negative 31 kg. If you calculate this, I think you will get 1.76 times 10 to the power 11 coulomb per kg. This is a standard number. This is charge to mass ratio. Okay, so sometimes we can do the experiment here also. Okay, we can measure this U over m. Okay, and the charged particle is moving in a circular path. So if T be the time period, then the time period is equal to 2 pi r. R be the radius of the circular path and v is the speed. So to calculate the time period, T equal to 2 pi r over v then. So using this, first calculate the v, you can calculate the v from here, then you can calculate the time period also. Or if you know the time period, you can calculate the speed. Okay, so this is all in this video. I'll bring the another video next time. Okay, thank you.